Okay, so next we're going to look at another extension to RNNs, which are the LSTM networks. So the goal here is that we want to have memory that can go back to earlier parts of a sentence. Now, if you look at the example sentences here, the young woman went to the movies with her friends, and then the second sentence starting in the same way, but then has this part in between, the young woman having found a free ticket on the ground, went to the movies. You can see that the relationship between the beginning and the end of the sentence now it's getting quite long. So for a network, it's going to be quite difficult to pick up the relationship between the subject, the woman, and the verb went. And it's going to be difficult for both a CNN type network or an RNN network. Even though in an RNN, we are feeding in one word at a time, because of the way it works, it's not going to be able to go back such a large sequence to make this connection here. So the extension that we want to do with an LSTM, the long short-term memory network, is that we have an additional memory state. And this can keep track of a core, the core thought, the core theme of a sentence, of a sequence that we feed in. So the way the network architecture looks like is we have the same one as before, an RNN type architecture with the recurrence in there. But now each neuron here has an additional memory state. How the memory state works exactly and how it's trained is a bit more complicated. You can look at some of the online references I linked to see how this works, but here we'll just treat it as a black box essentially and use it in a network that we're going to train. So the task that we want to be able to learn is text generation. So for example, in a chatbot, it has to be able to generate a new sequence of characters by remembering or learning from existing sequences it has seen before. So we need some kind of text to train it. And one good source of longer documents is Project Gutenberg. This is the online repository of free ebooks, so books that are out of copyright and you can legally download and use. And we're going to use some ancient Greek literature, Aesop's Fables, in English translation. So you can download this in various formats, including plain text that we can feed directly into a network. So again, the goal is we want the network to learn by reading existing stories, how to generate a new sequence of words. And this is done in a word-by-word fashion. So we start from one word. We give the network sort of the start of a sentence, and then it will predict the next best word. And then after taking this one, the next best word, and so on. And this way we can generate a new sentence or even a complete new story. So once we have the document, we do the standard pre-processing like before. Here we'll just use the basic tokenizer that comes with Keras. So we tokenize the whole set of stories that comes here, not very big, 237 kilobyte. So we're going to get a dictionary for each token and an index into the dictionary. And then we can encode a new sentence. This here is a start of a story, the fox and the grapes, period, a hungry fox saw. We can encode this sentence using an index into the dictionary. So for example, here, the word a goes back to the dictionary, and this is the encoding. So here we have the numbers we can use to feed it into the network. So the goal is a sequence learning problem. We want the LSTM to be able to predict the next word in a sequence. So if we give it as a start, the fast and then the network will predict what kind of word could come here. And just based on the learning samples, you know that certain words are a lot more likely to come here than other words. Now, for example, here, a noun would be a lot more likely than a preposition. So for the network that we're going to build here, we're going to use 20 word sequences as the context. And this is what we feed in as input. And the output from the network is a one-hot vector, which shows us the next word in the sequence. So the code that I used and that you can try out yourself as well, I picked from this GitHub repository. So again, this is how the network looks like. We start with a sequence of 20 characters. So the sequence here is the index into our dictionary. This goes into an embedding layer. And basically, we're building word embeddings here with a size of 100 dimensions. And then the output from this here goes into an LSTM layer. We are using an RNN architecture. So we are processing it word by word. So the next state of a cell depends not just on the current word, but also on the output from the previous word. So just like before. So it's a RNN architecture. And the new thing here is that we are using not plain RNNs, but RNNs with this additional memory state, the LSTM. So again, we can look at how we implement this in Keras. So we need a couple of different layers here, in particular, like before, a dense layer, but the new one here is an LSTM layer. We have an embedding size of 100. So we have our input layer, an embedding layer of size 100 dimensions. We have an LSTM layer with 256 neurons. Then we are adding a dropout layer and then a dense layer, which is connected to the output with a softmax. So then we are building our model using this network here with the input text, the output text, and pick up optimizer and can build the network. We let it train for 100 epochs, batch size of 32. And when you train this, well, first let's look at the resulting network architecture. So we have the input layer, the embedding layer, LSTM layer, and the dense layer. Doesn't look so bad, but again, remember, because of this training in the RNN, it's a lot more training effort than you would expect just from the size of the network. So you can see we have quite a few parameters, almost 2 million parameters to train. So you can expect this to run for a couple of hours before you get any result on 100 epochs. But once it is done training, you can, for example, look at the word probabilities. Now you feed in a sequence of words, and it can predict you softmax output, what is the most likely next word to come in the sequence. So here, the fox and the stag, there was a, and then it will predict as the most likely word time, second likely lion, third likely man, and so on. And even though we haven't done any kind of part of speech tagging or any other kind of language modeling, just from processing the input text, it picked up what kind of word is, or what kind of word category is the most likely here. So a noun, a verb, preposition, adjective, and so on. So, but we don't just want to look at the next word. We want to use this to generate new text. So again, we have to start. We give sort of as a seed phrase some input text to the LSTM, and then we let it predict the next word. And then once we have the next word, we can append this to the sequence, again, feed this in, and then again, get the next word predicted, and this way generate new sentences and eventually a whole story. When you do this kind of text generation, you will see that you have to apply a few tricks to get something interesting out of it. Because if you just always pick the most likely word here, the whole text becomes too predictable, too similar to the original text. And in most cases, you will see it goes into a loop where it just starts repeating the same thing over and over again. So just for the purpose of making this a bit more interesting, there are various tricks people use to basically not always pick the most likely one, but possibly the second most likely one. And then tricks to avoid having repeated sequences all the time. In one of the references in the lab, you'll get a link with a web page where you see a number of these tricks mentioned. And we'll do text generation, not with this network, but with another one. So you can try this out yourself. So here in this experiment, we're using a parameter called temperature, which essentially means the higher temperature we have, the more random the output will be. So lower temperature means more deterministic choice. We pick the most likely ones, and higher temperature, we are jumping to another word. And now, when you run this, you get a result that looks like this. So depending on the temperature, you can see the output looks slightly different. You can see that the second one looks a bit more creative than the first one. And you can also see that with this very simple approach, well, we get a sequence of words that sort of make sense. Running up, they found for you, said he had a way to make them. I will be a lion. So a couple of words are sort of okay, but as a whole story, it's not that convincing. And it has to do with both the very limited training size that we fed into the network, just this 200 kilobyte, and also with the fact that we used a rather simple network architecture. So if you want to improve upon this to be able to generate more interesting, more semantically coherent sentences and stories, we're going to have to increase both the training size and make the network a bit deeper than what we have done so far. And essentially, one way is to have a deeper network architecture. Instead of just using one LSTM layer, you can stack multiple LSTM layers on top of each other. But then obviously, you're going to have a lot more training effort because you have to propagate back not just through one RNN layer in time. This goes then back through multiple RNN layers. Okay, so much for this first example for text generation. We're going to look at another architecture here, sequence-to-sequence models, and then move on to the most sophisticated type of models, and we'll see how well they do with text generation. See you then.